Come on, everyone. Let's start off. Last thing we did was this field on an actual line of a ring. Great. Let's go ahead with a question. So there, the maximum value occurs at r by √2. So let's say we have a ring here, which is plus q and radius r. Gravity is there. At some height here, we kept a particle of plus q and mass m at a distance x from here. Particle is in equilibrium. Find x if particle is in stable equilibrium. I'll frame the question in another way. Find x if the particle is in equilibrium. That's a completely different question from find x if the particle is in stable equilibrium. Think, how will we do this? So we have a ring here of q and r. On the actual line, you kept another small charge q and mass m. It is in equilibrium. It is at rest. Find x for stable equilibrium. Is that a guess, right? Matlab, it doesn't matter which mass I keep here. All will be equilibrium there only. Means if I keep an elephant here or if I keep an ant here, they'll be in equilibrium at that position. That's what you're trying to say. Other scams on. So if I just ask you this question, find x for equilibrium, how many answers are there? There are two answers. Because see, look at this graph here. When you look at the graph here, there are two electric fields, EQ is equal to mg, which will occur 2 times, isn't it? Assuming it is not a maximum value, there are 2 times when this field will match the mg ka value. Is that making sense? So if you just write this thing, you will get like E into Q is equal to mg. That means when field ka value becomes mg by Q, the system will be in equilibrium. So you will get 2 times electric field, again assuming x is not the maximum value there. So this guy will be k q x by r square plus x square whole power 3 by 2. So if you solve this, you'll get 2 answers. We'll get x1 and x2. Is that clear? So there are 2 positions for equilibrium, but in among them, only one is stable equilibrium. So you can also argue this from a graph. So this graph which you get here, there are 2 positions here, x1, and there are 2 positions here, x2, for which you get the same amount of electric field. That means you can keep the particle at 2 positions to be in equilibrium. Is that understood? So they'll be on either side of r by root 2. But between both of them, there's only one in stable equilibrium, one is unstable. How do you figure out that part? You figured it out? Random guess. Figured it out. Okay. Others, what do you guys think? X1 or X2, which will be stable? But did you get the logic why there are 2 points? Because field is increasing and decreasing, so you'll find 2 times that value will come. Now, remember how to find something stable or unstable, what we do? We put it there and we displace it and see if it is coming back or not, isn't it? Now look at the scenario. So let's say if you take x1, let's say this point is x is equal to r by root 2. So this is where E is maximum. And let's say our equilibrium position occurred somewhere here. The particle is here, Q. Now, let's do this thing. If I push it up, what will happen? Look at the forces here, EQ, mg. If it is pushed up, slightly disturb it up. If it is pushed up, E increases, isn't it? Because if you're going towards r by root 2, maximum value will increase. Therefore, EQ becomes greater than mg. Therefore, it goes up. Is that making sense? Similarly, if I push it down a bit, EQ will decrease. Mg will become greater than EQ. It will keep coming down. So what kind of point is this? If you push it away, it goes away. This is unstable, right? In a stable equilibrium, if you push it up, it should come down. If you push it down, it should come up. Is this making sense, everyone? So whenever someone asks you stable or unstable, this is one easy way to figure it out instead of doing all that math part. So the other case, if you take plus q and r, let's say if this is x is equal to r by root 2, the maximum value, and let's say if the equilibrium occurs here now. Now look at this thing. So now the forces are EQ and mg. Now if I push it up, E will decrease. Mg becomes greater than EQ. It comes down. Making sense? Is that clear, everyone? There, check this out. So you'll get 2 answers. Basically that is right now, Vihan. You will get oscillator motion only stable equilibrium. Unstable में oscillatory होगा ही नहीं. Actually, it is the other way around what you're saying. Oscillatory motion occurs at stable equilibrium. The way you rotate is like oscillatory motion is stable equilibrium. That is wrong. You're getting what I'm saying? It is the other way around. A gives B, B doesn't give A. Is this clear, everyone? Got the question? So the question looks easy, like EQ is equal to mg, but the moment I add the word stable equilibrium, suddenly there's a confusion between 2 answers. Next one. We have a ring here, plus q, radius r. We have an identical ring, plus q, radius r. And let's say the distance is 2 root 3 r. So here we have a charge minus q and mass m. So it is given speed u. So I want this particle to go from this center A to this center B. Find u minimum if the particle goes from A to B. Find u minimum for the particle to reach B. Projected from center A as shown. Rings are fixed. Let's not move them. Already we have enough difficulties in life. Anyone got 0? If you got 0, you have created a energyless free travel. You are the pioneer of our future transport system. I'll give an analogy. See, what is this question like? I'll tell you a small story. Say. So whenever you're sending a rocket, let's say satellite or something, from Earth to Moon or Land rover or something, this is what they do. So initially, the rocket is like this. So the engine is backward. The rocket goes like this. After some point, the rocket is made to rotate 180 degrees. And then the rocket goes down. So they rotate the rocket at some position here. Why? Basically, this point is the null point. Meaning, when the rocket is coming here, the Earth attraction is stronger than the Moon. So you have to go against the Earth. And once you cross this point, the Moon attraction is greater than the Earth. So Moon gravity will dominate. I need to go down in the opposite direction. But imagine I just want to launch a nuclear missile to Moon and destroy it. And I want to give minimum speed. So you tell me up to which point should I send the missile? After that, it goes automatically. If I can send the missile till the null point, and all I need is a little push, and automatically it will go right. Are you getting the point? So my landing point or my final position is not the Moon. My final position is the null point. If I can send the rocket till the moon, then automatically it will go on its own. In chemistry, we call this thing activation energy. For example, if you have a reactants and products, like this is our question has become like this now. If this is the reactants and this is the products, if they're at same energy, why don't the reaction happen on its own? Because you need to provide some activation energy, isn't it? So even though the reactants and products look like their same energy, the reaction doesn't happen because you need to take it till this point and then automatically the reaction will proceed. So the minimum energy required to supply is not initial and final, but initial and the null point. Is that making sense? So using that thing, if you see in our question, what is the null point here? The center, right? Because it is symmetry, you can clearly tell this is the null point, which occurs at r root 3 and r root 3. That means if you can send a particle till the center, after this automatically, this ring will attract more strongly than that, automatically it will cross, right? I never said you should come to rest at B. The question is, with what speed should I throw? Should reach B. So the point is you need to reach the null point. So that will be there. So if the charge reaches the null point with a small velocity, negligible velocity, right, then it is automatically attracted towards B. So this is my state 2 and this is my state 1. Is this clear, everyone? Then energy in state 1 is equal to energy in state 2. Law of conservation of energy. Now, last time only we discussed this. The moment I use the word, I'm starting here, I'm reaching here, you're talking about what? Initial and final position. And among the two set of weapons we have, force and torque equation conservations, it is clearly telling you, boss, use conservation. Energy conservation. So initial energy is equal to final energy. Now, this is the second trap, okay? The first trap is this null point. Second trap is this. Initially, what is the energy? Half mu square. What is the potential energy? Potential energy is potential at a point into the charge. What is the potential at point A? K Q by R due to this ring plus K Q by due to this ring also you have to take, isn't it? When you say potential at a point, it is due to all charges present in the space. This ring ka potential also you have to include. Most people forgot, they keep forgetting the second ring. Generally, that's what people forget. How much is this thing here? This is r square plus 2r root 3 square. So root over r square plus 2 root 3 r ka square into minus q. This is your initial energy, everyone. This is due to the ring A ka potential. This is ring B ka potential. I'll just do one thing with ring 1, ring 2 at point A. So don't forget this thing. This is equal to, you reach the null point with a negligible velocity. So you can say V is almost 0. So kinetic energy will be 0 plus. Now what is the potential energy here? K Q by, now that distance, root over r square plus r root 3 square into minus q into 2 times, because there are two rings. यहाँ पे भी दोनों का potential लेना पड़ेगा ना. So every point you have to consider two potentials due to both the rings. Is this understood, everyone? There you got everything there. Solve it, you'll get Yuga answer. So into 2, because there are two rings. The most common mistake is people keep forgetting there are two rings. They do only for one ring. The solving part is fine. You can put the numbers and finish it off. You know everything here. You know this full term, you know this full term, you aa jayega. Any doubts on the equation, please ask. So these are the two things. One, you need to send only till the null point. Number two, you need to take potential due to both the rings at point A and the null point. So actually B is useless in the story. Somehow you can reach B, automatically you'll go till B. To reach the null point, you'll automatically reach till B. Any doubts on this? So this is a pretty important concept, reaching the null point. Keep this in mind. You will have questions based on this. You will see in different chapters. You will see this in gravitation also. You'll see in electrostatics. This is the main idea. Chemistry activation energy type. If you can reach the top of the hill, after that it will roll down automatically. Clear? Next one. Kritik, clear with this? Clear na? Abhinav? Arush? Clear? Vignajit? Ojas? Surya? Next one. Go ahead. Going ahead. I'll leave this for you. One of the fine art. We have a uniformly charged disk. Sigma is the surface charge density, radius is R. So we have a point P here. Let's say this distance is Z. Find the field at point P. Find field at point P. Then explain the result. If you make the radius of the disk infinity. Once you got the result for the first part, if I put R is infinity in the result, something happens. What does it mean actually? What did you get then? Let's get the first part. One thing I'm sure you figured out, it is integration. You take rings upon rings and then you integrate. Get this, you got 2-3 minutes. How do we choose an element? At a distance x from here, I will take a thin ring like this. Whose thickness is dx. So area of this thin ring is 2 pi x into dx. Everyone knows that, right? I hope everyone knows that thing. So circumference into thickness. And if you want, I can just show you that once. So if this is x and the thickness is dx, and if you take a scissor and cut it, you will get a thin rectangle whose circumference will be 2 pi x and the width will be dx. It becomes a small rectangle which is length into breadth. Okay, that's how you get this. Then what is the charge on the ring? Charge on the ring will be sigma into area of the ring, which is 2 pi sigma x dx. Now, due to this ring, you're trying to find the field here, and this is z. So we are using the field on the axial line formula. So field due to the ring, what is the formula? K, Q of the ring, Z. Again, go back to the formula in case you forgot. This was the result. K, Q, X. X is the distance from the axial line by r square plus x square 3 by 2. Be careful, I used x for this, so it could be a little confusing. So K, Q, Z by the radius of the ring, x square plus z square whole power 3 by 2. This is the field due to this one ring, which is K, Z, Q of the ring is 2 pi sigma x dx by x square plus z square 3 by 2. Remember, z is constant here. So E of the disk will be integrate all these rings. There, if you got till here, the physics part is taken care of. K is 1 by 4 pi epsilon. That will be z 2 pi sigma integral. Limits will go from 0 to r. X dx by x square plus z square whole power 3 by 2. Now, how to integrate this? In physics, if you ask me, primarily there are two main techniques. Integration by substitution is one. So you will learn this in max, I think. Did they start integration for you guys? Differentiation start ho gaya na, at least. Not started. So calculus should have been started. Okay. You will learn this thing. So how do we integrate this? We use integration by substitution. So I'll just show you this. Nah, I would have shown you anyways. But remember this thing. This might look little tough and all, but once they actually teach you, this is a joke. So if you have got till here, the physics part is taken care of. After that, we can assume you will know how to do this. So put x square plus z square is equal to, let's say, some t square. So you have to find a good thing to substitute. That you will learn in max, y and all. You will see. Now differentiate on both sides. If you differentiate on both sides, this guy will become 2x dx. Z is anyway constant. It will become 2t dt. Right? And when you put x is equal to 0, we will get t is equal to z. And when you put x is equal to r, we will get t is equal to root over r square plus z square. So now your integration will become E of the disk 2 pi, that will cancel, sigma z by 2 epsilon integral. So denominator becomes x dx is t dt. Denominator becomes t square ka this thing t cube. And limits will go from, so basically 0 ka place mein t will come now, z. And r ka place mein will get root over r square plus z square. Can you see the integration became easy? It simply becomes 1 by t square ka integration. So that is the technique here, integration by substitution. And if you remember, last time we did something like this for this guy. Isme we did this thing, tan alpha is equal to x by d, and then we differentiated. This is also integration by substitution. If you ask me physics, generally these are the two main things which keep popping up. If you are comfortable with this much, I think you'll be able to handle maximum integrations in physics. But compared to max ka integration, right, this is like a small stray puppy on a road. Just imagine small puppy like which you can keep on your hand and it is walking on the road. It is like this. Max में they'll teach you a dinosaur and a Godzilla. Clear with this? Then we still have to integrate this. I'll just write it down again. So E disk will be sigma z by 2 epsilon integral. This guy will become dt by t square. Limits will go from z to root over r square plus z square. That is minus 1 by t ka integration. sigma z by 2 epsilon minus 1 by t limits z to root over. Substitute here, we will get sigma by 2 epsilon, z will go inside. Okay, let's keep z here. So this will be 1 by root over r square plus z square minus plus 1 by z sigma by 2 epsilon 1 minus z by root over r square plus z square. It looks a little difficult to remember. I'll give you a better way to remember this thing. So that this is the final result for their E of the disk. But a better way to remember is this. So when you have taken the disk, this is the point P. So this is the field E here. This is angle theta. This is Z, and this is your radius R, and this guy is the hypotenuse root over R square plus Z square. You can simply write this thing as sigma by 2 epsilon 1 minus cos theta, where theta is this half angle made by the disk at point P. This is more easy to remember, right? Instead of Z and everything, this will be a much easier formula to remember. There. So if you can remember it is 1 minus cos theta, it will be easy to figure out from the theta that you can calculate from the dimensions. Is that clear, everyone? Check it out. So main thing physics got over here. If you got till here, your job's done. This is a better way of remembering the result. Sigma by 2 epsilon 1 minus cos theta. Then what happens if we make R infinity? Right, Falak. If you make R infinity, the disk suddenly becomes an infinite sheet. Isn't it? It'll occupy the whole space, isn't it? So there is a never-ending sheet. The disk will never end. Matlab kya? It's an infinite sheet, isn't it? It's covered everywhere with a big sheet there. And look at the result. What happens if R is infinity? This term will become 0. Then we will get the field due to the infinite sheet. Sigma by 2 epsilon. That is the field due to the infinite sheet. So how will the result look like? So if this was a sheet, sigma, so the field, if you see, it is independent of the distance. No matter how far you go, the field will be constant. It will be pushing away sigma by 2 epsilon and sigma by 2 epsilon. So the field due to an infinite sheet is a constant value. No matter how far you stand from an infinite sheet, the field will be always constant. Is that clear, everyone? So from the disk, you can get a result of an infinite sheet. The field is away from the sheet for positive and negative, it will be towards the sheet. Is this clear, everyone? Now, at a mains level, the result is more important. At an advanced level, you should know how to integrate, because what they will do, right? They'll simply say like this. We have a disk here where sigma is equal to sigma naught r. मतलब charge density भी r के साथ increase हो रहा है. मतलब at the center there is no charge. Here there is a little more charge, more charge, more charge, and more charge. So density is increasing. As you go outside, the density is becoming bigger and bigger and bigger. So you won't be able to handle this without integration. Clear, everyone? Clear path? There is no mathematical thing. There's a non-mathematical explanation. I don't know because it is infinite sheet. I don't know. I couldn't figure out. If you have something, let me know. Certain things you couldn't explain. Meaning, until unless you kept R infinite, even we didn't realize, no, you're going to get a constant result. Next one. So how they can try my question on this infinite sheet? Let's say we have an infinite sheet. Sigma. So they will say a particle is projected with u at an angle theta, which is minus q and mass m. And let's say gravity is also there. Find range. So there'll be some easy questions. So they'll mix up this infinite sheet with something. So we have a pendulum here, mass m, length L, charge q. Gravity is there. You placed an infinite sheet below it. Find the new time period. There, get them. Easy ones. Yeah, you just have to dump G effect and you'll get the answer. और कुछ नहीं था concept, बस वही था. So in this case, if you take the particle, what are the forces acting on this? You have your gravity mg. We also have EQ. So this particle will think the net force mg plus EQ is equal to m into G effective. Because the particle doesn't care whether the force is coming from field or gravity, right? And we know the range ka formula is what, u square sine 2 theta by G effective. Similarly here, this is tension. This is mg. Again, we are assuming tension is not becoming zero. There is a possibility. What is E ka value? Sigma by 2 epsilon. So here tension will be mg minus EQ. If tension becomes zero, then the time period is undefined. It becomes infinite. It will just float in the space. This is m into G effective. So again, same thing. The pendulum won't think, there's an EQ force. It will simply think the gravity must have decreased. So G effective will be GQG minus EQ by m. Therefore, the time period will be 2 pi root over L by G effective. Clear with these things? These are the kind of questions you'll get in mains, like some easy ones. So the thing is, you just created a sheet that gave field and that messed up the G effective and that changed the answer. Not tough, but yeah, you have to think. Yes, and I directly will get the answers without thinking. Easy? Any doubts on this page? All got this. Next one. We have a uniformly charged hemisphere. Let's say charge density is sigma and radius is r. Find the field at the center. Hope you remember how to choose elements for a hemisphere. This is the third time you're saying. First time you saw in hemispherical elements are where? Center of mass. Then moment of inertia. This is the third time. Again, you will see this in magnetism. You could have actually seen this in fluid mechanics also, but luckily projected area saved you there. The moment you see an hemisphere, मतलब क्वेश्चन क्या है वो अलग से बात है. मतलब you should know boss इसमें एलिमेंट ऐसा होगा. If you're that comfortable, right? Physics में integrations you will just, it will be like a walk in a park. The biggest problem is people say a thing and they don't know how to choose elements. So just to give you an idea there. So that's why I keep saying these questions, right? After the class gets over, today or tomorrow, sit and try to do them again on your own with a rough paper. There. This is the first time we saw hollow hemisphere, center of mass rings. How did we choose an element C? At an angle theta, take a small ring RD theta. This is the element. This is the area. Independent of the chapter, this part of this is constant. Can you see how we did choose the element? Then we also saw this thing in rotational mechanics while finding moment of inertia for a hollow sphere. Isn't it? You're seeing this for the third time now. Try. I'll give you 2 minutes. Just try. Any answers? Let's see. You can integrate, Purva. You get a very good integration here. Let's see. So from the center, at an angle theta, take a small slice d theta, we get a ring like this. You know how to visualize this? Imagine this thing. Take a watermelon, ठीक है, उसको horizontally 2 बार कट करो तो एक डिस्क आएगा. Now in that, remove the red color part from the middle. You will be left over with a green color band, right? Able to visualize? That is how it would look. So we will get a ring like this. So this is radius r, this is theta. So this distance will be r sine theta. This radius will be r cos theta. So this is the field on the axial line. So if I cut this ring, I will get a thin rectangle. जिसका length will be 2 pi r cos theta. And this width will be r d theta. So we get area of this ring will be 2 pi r square cos theta d theta. So charge on the ring will be sigma into 2 pi r square cos theta d theta. Right, Falak. K का ना नहीं अंश, that is not right. ना K को 1/4 पे epsilon लिखो. We'll get a more simplified, better form. There. So now this is the center there. We are going to use the field on the axial line. So what is the field ka formula? So the field due to the ring will be K, charge of the ring, Z, which is r sine theta, by r square, the distance square basically, r cos theta square, r sine theta square ka 3/2. The denominator become actually r square, isn't it? So this will be K sigma 2 pi r square, एक और r है तो r cube sin theta cos theta d theta by denominator is r cube. This thing turns out to be 1 by k is 1/4 pi epsilon sigma by 2 epsilon. नहीं 2 अंदर बेस देना, so k sigma pi sin theta cos theta will become sin 2 theta d theta. 2 sin theta cos theta na. Right, you got it. So the field due to this hemisphere will be integrate all the field due to the rings. K sigma pi integral sin 2 theta d theta. Remember here, when you're at the bottom, theta is 0, and as you go up at the highest point, you'll get theta is 90. You'll cover all the rings there. Limits will be from 0 to 90. Sin 2 theta will be minus 1/2 cos 2 theta. Limits will be 0 to pi by 2. That will be cos 180 is minus 1, and that is 1, that is gone. So k sigma pi, k is 1/4 pi epsilon. So sigma by 4 epsilon. There, that's your result. Is that clear, everyone? Now, so it's a good result to remember. Sigma by 4 epsilon, this thing looks like that infinite sheet ka half of it. But you can do something better with this. So instead of a full sphere, let's say if you're only part of the sphere, like this. It's not that difficult to solve. What will change here? limits will be, suppose if this is theta, so here the limits will be, remember you took here theta is 0, so this guy will be 90 minus theta, so this limits will be 90 degrees, isn't it? So in this integration, limits will be from 90 minus theta to 90. So you will do that. So the result will be E is equal to sigma by 8 epsilon 1 minus cos 2 theta. Clear with that? Where theta is the vertical angle there. So if I put theta is equal to 90, I'll get sigma by 4 epsilon. Clear, everyone? So this will be a part of a sphere. So I am taking theta with the vertical in this formula. If I take with the horizontal, I think I'll get something else. I'll get 1 plus cos 2 theta. There, have a look at this. Any doubts on the integration? Clear with this? So every time you might not get a hemisphere, I can get a part of an hemisphere also. Any doubts on this? The next one. Now the next one which I'm teaching you is quite important. The results are really important. You should definitely mark this up. I would want you to write it down because I observed in mains, right, whenever they asked questions on electrostatics and gravitation, at least 4 out of 10 times the questions are based on this hollow sphere and solid sphere results only. So if you have a hollow sphere, charge q, radius r, where r is the distance from the center. So E will be, the field inside is 0. The derivation we'll see this in Gauss law. So the field inside is 0. So this is for r less than capital R. So this is for the points inside. That means if Earth was actually a hollow sphere and there's no material inside, and if you throw inside, you will actually float. The points outside, kq by r square. This is one good thing. The points outside will behave as if there is a charge at the center. So points outside, the field is like a point charge. So if you try to plot the graph for E versus R, the field will be 0, then suddenly bumps up, and then it goes like, it's a discontinuity. Similarly, the potential thing will be, potential inside is kq by capital R. Remember, R is the radius of the shell. So for inside, it is constant. And for outside, it behaves like a point charge at the center, R greater than R. So if you try to plot the potential versus R graphs, it will be constant for some time. That is still the center R here, and then it drops. Check out the graphs. Put it down. Everyone should note down this. Clear, everyone? Next one. Uniformly charged solid sphere. So the charge is everywhere inside. So the field will be K Q small r by r cube. It actually increases linearly. And outside it behaves like a point charge at the center. And you can think about that also logically. Think about these things. If you're standing here, then what happens? All these charges are pushing you outside. All these charges are pushing you inward, so they're canceling out, right? But if you go and stand on the surface, what will you notice? If you stand on the surface, everyone is pushing you out, isn't it? So if you try to plot this graph, you'll notice the maximum value will occur on the surface. And then again, it drops off because the distance is increasing. So if you plot this graph for E versus R, the field increases linearly till the surface and then it drops. Now, even among these, 8 results, this result is even more common, the potential. KQ by 2R cube into, it's weird, but that is the reason most people don't remember this result properly. Comes a lot. Matlab, I think in JEE means, right? This was a direct question. Find the potential at R by 2. And your idiot seniors, some of them didn't do income because they forgot the formula. I think even in this current batch, right, I must have asked them this formula in the last 4 months at least 7 to 8 times. And I scolded them half of the time. So I'll do the same thing for you guys also. Remember this thing. This is something I'll keep asking you and I'll keep scolding you for not answering. Comes a lot. Because same thing will come in gravitation. Sirf K ka place mein G dal do, Q ka place mein M dal do, and there you got a formula. This will be KQ by R for R greater than equal to R. So, and one important thing here, so most people think potential at the center is 0. It is not. Potential at the center, if I put small r is equal to 0, this will be 3kq by 2r. So if you try to plot the graph, so this thing is actually a parabola. And here the value is 3kq by 2r. Remember, potential at the center is not 0. It's an r square function. So this is actually a parabolic going downward and then it goes down. Copied, put on the results. Clear? Copied, everyone? Let's see a question. Let's get used to these formulas. So we have a solid sphere plus q and radius r. This is plus q and 2r. So we have a solid sphere and a hollow sphere. It is encloses. It's a hollow shell. This is a concentric solid sphere. So they have a common center. So O is the center. This is point A. This is point B, and this is point C. So O to A distance is r by 2. O to B distance is 3r by 2. O to C distance is 5r by 2. Find the field and potential at OABC due to the hollow shell and the solid sphere. This will cover all the 8 formulas. So I wanted to find the field due to the hollow shell. I wanted to find the field due to the solid sphere and add them vectorially. Take a minute, try one, getting it. Then I'll show you one and then I'll give you time to do for the rest. Get them all. I'll show you in a minute. Let me show you what I'm trying to ask you. So I will find the result due to the hollow shell and the solid sphere C. First thing, field at O. This is what you need to ask yourself. Where is O for this hollow shell? Hollow shell, inside or outside? Inside. What is the inside formula for hollow shell? 0. So this guy is 0. Understood what you're doing? So first thing you need to ask, where is the point? Then you have to see what is the formula. Then apply the appropriate formula. For the solid sphere, where is point O? Inside. Where? Center. Field is 0. Add both of them. 0 plus 0, 0. So there's no field at point O. Next thing, potential at O. For a hollow shell, what is the, where is point O? Inside. For inside, what is the formula? KQ by radius. Remember, but radius has become 2r. Don't write KQ by r. The radius of the hollow shell is 2r. For a solid sphere, what is the potential at the center? It is not 0. It is 3KQ by 2r. Add both of them. You'll get the potential at the center. Are you getting what we're doing? Let me show you one more. Field at point A. Where is point A for the hollow shell? Inside. So what is the field? 0. Where is point A for a solid sphere? Inside. What is the formula? KQ by r cube into the distance, which is r by 2. So if you just add these two, you'll get the final result of that. Are you getting what I'm asking now? So see where is the point for the hollow sphere, for the solid sphere, put the appropriate formula, add both of them, and you're done. You'll get the final result. Now can you do for the rest? Get them. I'll give you another minute and a half. Anyone confused what I'm asking? So the main thing is that only. That's it. Doesn't matter. I can give you solid sphere, I can give you shell, I can give you shell, I can give you shell, I can give you 10 shells like this. Every time you need to ask the same question. In this case, luckily, or in the same direction, na? So it adds up. This would be I cap because B is on the right hand side. Potential में problem नहीं आएगा. Field you have to be careful. Get this thing. Potential at A, B, C. Get them all. I think if you got all of them, you're done. You will know all the 8 formulas. Done. Finish off. Finish off. Then I'll show you all the results you can verify. Let's see. Potential at A. For the hollow shell, it is inside. So KQ by 2R. Point A is inside this. Remember that big formula which you'll get KQ by 2R cube into 3R square minus R by 2 whole square. Then EB, this is still inside. Now this guy is outside, so K cube by 3R by 2 whole square I cap. Potential at B, now this is still inside, so K cube by 2R. So hollow shell in that sense it is neat, and this guy will be K cube by 3R by 2. Clear? And then similarly for EC, it will be K cube by 5R by 2 whole square. Now it is outside. So once you're outside, it is done then. Then just like two point charges in the center. You can actually replace the whole thing with 2Q at the center and finish it off. Potential at C will be KQ by 5R by 2. KQ by 5R by 2. Easy? Any doubts on this? All clear with the steps? Clear with the formulas. Na? So the main thing is that only. Meaning, see, this was actually a P by Q. Huh? Find the potential at R by 2. That was a JEE mains question. Not even shell and all that stuff. Next thing. We have a solid sphere. Someone made a thin tunnel. Plus Q and radius R. You dropped a particle minus Q and mass M, so released into this thin tunnel. So let's call this point A and C is the center. Find the speed when it reaches point C and the time taken to go from A to C. Find speed and time when it reaches point C. This thing we'll do in gravitation. We'll do more variations of this. For now, we will do one. How do we start this thing? Look at this. Again, same story. I'm asking you when you reach point C. Matlab, indirect, I'm telling you A is the initial point and C is the final point. So define this. This is my state 1 and this is my state 2. Initial energy is equal to final energy. Remember, potential energy is potential into charge. So initial energy, kinetic energy is 0. So potential energy on the surface will be kq by r potential into minus q is equal to potential at the center is how much? 3kq by 2r. Be careful, it is not 0 plus half mv square. बस इतना ही करना था. So this here is potential on surface. So instead of using mgh, we are using kqq by r. This is potential at center. To solve this, you will get Vc is equal to kqq by 2r. So root over kqq by mr. Easy. What about the time? If the particle is somewhere here, the force acting on this will be q into e. Let's say this is at a distance x. So look at the particle, the forces. So force will be the field, which is k q minus q by r square into x. Isn't that the field? Right, field is, let me write like this, q into field will be k q x by r cube. This is equal to mass into acceleration. Acceleration is equal to minus k q by mr cube into x. There, your favorite thing is back. This is your omega square. This is an SHM. So this particle will actually keep oscillating front and back without stopping, isn't it? Once it crosses the mean position, it will start decelerating. It will go to the other edge, stop, and come back again. So time will be 2 pi root over mr cube by kqq. But I am asking you the time only from A to C, right? So for the full oscillation, that is from this A, this center, this is the corner B, the time is T. You want only time from here to here. How much will that be? T by 4, isn't it? 1/4 of an oscillation. A omega से भी कर सकते हो. Yeah, you can do that. मतलब ना, if you figure out it is an SHM ना, then it is easy. A omega से आ जाएगा. हाँ, but अगर आप SHM करके, if you didn't figure out it is an SHM, then energy is the only way. But I think ना, the moment I ask you time, that should have given you hint ये SHM है, then you could have figured out. Is this clear, everyone? All got this? Take a break. Come back by 7. We'll continue from here. Any doubt so far? Chalo, come back in 10 minutes.
मुझे तुमको एक बात बताना है.
Chalo, let's go ahead. Let's see an easy one. So if you have a charged hollow hemisphere, this is positive charge, something here. This is the center. So instead of center, if I take any random point somewhere here, A. So this is how they'll ask a question. So let's say we have arrows here, 1, 2, 3, 4, 5 ASA. There are 5 arrows like this. So the question would be, A is any point on the that circular thing, but not the center. So which of the following direction represents the direction of field? So the question is this: what is the direction of the field at that point? 1, 2, 3, 4, 5. There are 5 arrows like that. How do we do that? Hmm. 2, 3. Let's see. Now, first of all, we don't know how is the field. That is the first thing. Now, when you don't know about the field, then you can always do this thing. So the point A, you can always assume there are two directions of field, Ex and Ey. Do you agree with this thing? So you can always take two perpendicular directions. Ex can be positive or negative, Ey can be positive or negative. So whatever is the field at point A, there will be two directions. Now, similarly, if I take one more hemisphere, by symmetry, you can say at this point also, this field will be Ey and this field will be Ex. Agreed? Now, if I combine both these hemispheres, I will get one full sphere. So from this argument, Ey will cancel. At this point, you'll get the field 2 times Ex. But what is the field inside a hemisphere? 0. Therefore, Ex must be 0, isn't it? So no matter which point you take on the surface, the field has to be downward. Magnitude we can't find, but direction that we can figure out. So all the points on this disk will have field downward. Is that making sense, everyone? So let the field be Ex and Ey. Take one of them and join them. Net is 0. The only way this is possible, Ey to anyway will cancel, Ex will not cancel. They will add up actually. Is this thing making sense, everyone? How much is that value we can't find, but this is how you do. Any doubts on this? Next one. Let's say we have small mercury drops of potential V. So each drop has a potential V. Now what you did, you took n of them. You took n drops and you combined them to form one big drop. So each one has a potential V. This also forms a spherical drop. Find the potential of the big drop. Remember we did something like this in surface tension. How do we do this? Let's see. Hmm. Right, Poroja. So when you combine these n drops, let each drop have a charge q. So V will be k q by small r, and let the radius be r. So I don't know q, I don't know r. So when you combine them, what will be the charge on the big drop? This is the mistake people do. The charge on the big drop is nq, isn't it? Charge won't remain same. If your each drop ka charge is q, then the big drop ka charge will be nq, and this radius is capital R. So law of conservation of charge is conserved. Second thing, volume is conserved. N times 4 by 3 pi small r cube will be 4 by 3 pi capital R cube. So we get R is equal to n to the power of 1 by 3 into R. So what is the potential of the big drop? K, the total charge n cube by the radius capital R. This guy would be n by n to the power of 1 by 3 k q by small r, n to the power of 2 by 3 into v. That's your answer, everyone. So charge becomes n times and radius becomes n by 1 power 3. So you have to conserve volume and you have to conserve charge. Is this clear, everyone? It's a good one. A little tricky, but yeah. Is this clear, everyone? Next one. Turn in the page. This is a very important result. I definitely wanted to remember this. We have a solid sphere with a cavity. Now remember, again, technically you can't see the cavity, but I'm just drawing it in 2D there. This is a solid sphere with a cavity. Rho is the volume charge density. O is the center. O dash is the center of the cavity. Find the field inside the cavity. Means if I take any random point inside the cavity here or here, what is the field? It's a pretty good result. Should definitely mug it up. They can also ask in mains as a theoretical questions. It doesn't matter the size of the cavity. इतना ही दिया information. You have only know the O and O dash. मतलब you know this vector O dash ये vector पता था आपको. You know this O dash vector. You don't know anything else about it. Think about it. Give it a try. Radiuses are not given. Q is not given, right? Roja, रो ही दिया ना. Where is Q? Right, Palak. That's a standard result which you should remember. So forget about all this thing. First of all, when you see a cavity, how do you even approach the problem? Remember? First time when did you start encountering cavities? Center of mass. And how did we do this thing? We said take this whole thing and then subtract the small thing, or we said take this thing and add this, you'll get the whole thing, isn't it? Now, see, that's what I'm saying. Try to understand what is the common theme there. See, same thing, moment of inertia for a cavity. What did we do? We took the full one, we took the small one, and then we subtracted, we got the answer. So it doesn't matter what chapter it is. The moment you see a cavity, the idea is take the full one and take the cavity and subtract, then you should get the answer. Is that making sense? So that is a general theme. So I will take the full one because full ka result I know. Then I will take the cavity one. That is also solid sphere. I know the result. If I subtract these two, I should get this guy. Right? Now, before jumping ahead, we know the field E is how much? E is equal to K Q small r by r cube. This is the r bar vector. So I can write this thing as 1 by 4 pi epsilon r cube. Charge is nothing but rho into volume 4 by 3 pi r cube. Sorry, into r bar. 4 pi r cube will cancel. So you'll be left out with. So field is equal to rho by 3 epsilon r bar. This is another way of writing the same thing in terms of rho. Charge diya nahi na. Now look at this. This is O. This is O dash. This is some random point P. You want to find field here. So in the picture, this will be O. This will be P. This will be O dash, and this will be P. Make sense? So for this guy, the field will be E1, which is rho by 3 epsilon. R bar is nothing but OP bar. Understood? So I don't know charge, right? So I brought everything in terms of rho. For the second guy, the field will be how much? E2 will be rho by 3 epsilon. So from center to that point, this is the vector. So which is O dash P bar. So now field at point P will be E1 minus E2. This will be simply rho by 3 epsilon OP bar minus O dash P bar. I can rearrange this. This will be rho by 3 epsilon OP bar plus PO dash bar. This will be nothing but rho by 3 epsilon OO dash bar. So the field inside of the cavity is actually constant. We'll write on the next page. It only depends on the distance between the centers. You take any point inside the cavity, the field is constant. Just look at the proof how we did this thing. First of all, in the question, Q is not given. So I have to eliminate Q and get everything in terms of rho. And when I did that in rho, I got a pretty neat result. Rho by 3 epsilon R bar. R bar is a vector from the center to the point where you want to find the field. Again, this is for only inside. Huh? So I have taken some random point P. So the full sphere is giving rho by 3 epsilon OP bar. The chota sphere is giving rho by 3 epsilon O dash P bar. If I subtract these two, I should get the field anywhere inside. Which turns out to be O dash. P got eliminated. Is this clear, area? So this is the final result. So let me just put it on again. And did you notice something? That result is actually independent of the size of the cavity. So if this was O and this was O dash, so the result is like this. All the field vectors are parallel to this vector. You're getting how is the field? So the field is parallel to OO dash. So the field here will be E inside cavity is rho by 3 epsilon O dash bar. This is a constant value. Definitely mug it up. Direct question you can send the exam. Standard result. So meaning if I had make a cavity like this, na, chota cavity banaya, field is same. If you make a big cavity, the field is same. It doesn't matter how big the hole you make inside. As long as the centers are at the same place, you'll get the same answer. So if I have to give an example, so let's say this is O, and let's say this is O dash, and let's say O dash is R by 4, and then the field inside will be rho by 3 epsilon R by 4. Direction will be O dash cap unit vector. Bas wahi tha. You have to get them. So it will depend on the distance between the centers. The formula depends on distance between the centers. It doesn't depend on how big the cavity is. Is this clear, everyone? So you know how they can ask you this in a more than one choice question? If a particle is projected inside the cavity, let's say a charged particle minus q and m is projected inside, what will be the trajectory of this particle? Circle, straight line, parabola, hyperbola. It will be parabola, na? Because the field is uniform, this will behave like a constant gravity, isn't it? So we have a uniform field. So it becomes like a projectile motion. So this path would be a parabola. If you project it along the field, it can be straight line also. Is that clear? So you can play questions like that. A particle is projected from this part, it goes and lands here. Find the distance between the centers. हो गया ना question? So you can include projectile motion inside the cavity. You can play around like that. But for that, you should know this result. Keep this in mind. Same thing we will see in gravitation again. It will be the exact same thing. All clear with this? Next one. We have a uniformly charged sphere. Now we know the like charges repel each other. So density is rho and radius is r. So if you look at this point here, this guy is repelling it, but repelling. So everyone is pushing every other one, isn't it? Imagine like this. If I put 50 people, right, in a room and everyone hates each other, what will happen? The entire room will start fighting with each other, isn't it? So there's a lot of pressure that builds up. So I want you to find the pressure at a distance x from the center. If every charge is pushing inside, they start generating pressure inside because this thing can't explode, isn't it? The sphere will be under tension. It will try to expand, but you're not letting it expand. So charges on the sphere, they repel each other, generating pressure inside. Find the pressure as function of x. So the first question, this will be an advanced paragraph. Find pressure at a distance x from center. X less than r. Second question, find the force on the right hemisphere due to the left hemisphere. So if I divide this into two pieces, so this left and right are both are pushing each other. Find the force on one hemisphere due to the other. Let's get the first one. Won't it be EQ by surface? But charge is everywhere, na re? Think. What you said, the idea was there only, but you can't just do that directly. Integrate तो करना पड़ेगा. Which surface will you take? See, अगर आपने यहाँ पे surface लिया, understand one thing. It will be like this, isn't it? There is an inner surface, there is an outer surface. It is being pushed from both the sides. Think. Take a minute, then I'll show you.
The net force, right?
Where? On whom?
In the layer.
When you find pressure, are you finding force on that or are you finding tension at that point? You need the tension on the surface by area of the surface, right? So do you think the tension will be only the force? ऐसा सोचो ना पूरा जैसे. Think of like this. This guy is pushing this guy.
Yeah.
But they can't separate each other because they're connected by a bond. So ये force F1 इस पे act करेगा center पे. Agreed?
Right.
These two people are pushing this guy out with F2. But these two can't get separated. So question कैसा हो गया पता है? Think of like this. We have charge Q connected by a thread, charge Q connected by a thread, charge Q connected by a thread. So this guy is pushing, this guy is pushing, this guy is pushing. All these tensions will add up, right?
Yeah. Oh, pressure is a scalar. Yeah.
So it just keeps on adding up pressure every point, right? Everyone is pushing. Think of like this, everyone. Let's say you are standing here. This guy is pulling it. This guy is pulling this guy. This guy is pulling this guy. This guy is pulling this guy. Who feels the maximum pressure? The center, isn't it? Everyone is trying to pull him out. The repulsion is trying to pull them out, and the tension is actually pulling in. See, that is the reason the sphere is not exploding. There are internal forces which are balancing this repulsion. So those internal forces will generate tension. That tension will generate pressure. Think about it. Take a minute. It's fine if you don't get it. You should know how to approach this. But this is what you will see in advanced paragraphs. So Vihan, if I tie you to two elephants and pull you with equal force from both the sides, you will have zero pressure. So if I tie you to one elephant here and pull this way and tie you to another and pull this way, since the net force cancels out, you feel zero pressure. You'll be very comfortable, happy, and yes, I want elephant massage, something like that.
Sir, but they are pushing away, right? Because all
They're
are
pulling out,
falling.
na regard. Na, see, think of like this. There's a molecule, there's a bond between them. Because of the repulsion, there's a tension in this bond. That is generating pressure, na?
Okay.
Let's see. Suno everyone. Now, these things, right? You should have seen this kind of techniques once. Like, not. So I'll take a small piece here. Like this. You're getting it? So I'll take a small area. Here a distance X. I'm exaggerating the figure here. Area A, and let this thickness be dx. So this piece will look like this. You're getting how it is? कभी आपने ये देखा when you go to a watermelon seller and ask him, अरे यार ये watermelon अच्छा है क्या? What does he do? He cuts a piece like this, isn't it? With a knife, he cuts this piece and he opens it and shows it to you, na? And then he puts it back. Able to visualize that? So if you remove the red color part, isn't this what is left out? Or green color patch? Able to visualize the element now? I know I gave very weird examples, but yeah, helps. So here this guy is dx and this guy ka area is A. So the volume will be area into dx. The charge on this piece will be rho into A into dx. Now, what are the forces acting on this? So this guy is pulling with tension T. Who is this one? There is one more slice here, na? This slice is pulling that one, isn't it? You're touching the inside part that is pulling with tension T. The outside one is pushing with T plus dt. And in this process, you're also getting repelled E into Q. You're getting what are the three forces acting on this? Just imagine like this. If you're standing in a queue, the guy behind is pushing you. The guy, in this case, they're pulling. The guy in front is also pushing you, and there's a repulsion force. You're getting it? So when you draw an FBD, there's a force at the back, there's a force in the front, and there's a repulsion force. So from here, you can clearly see T plus dt plus EQ is equal to T. We'll get from here dt is equal to minus EQ. There. We thought tension is increasing, but in reality, tension is decreasing outside. That's kind of obvious. The more you go out, the less and less will be there. Now, what is pressure there? So if I divide by area, dt by area, this becomes pressure, dp. So this is a small change in pressure because of this repulsion force. So basically, this is additive. So every piece will generate an extra pressure dp, 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 dp. You're getting it? So it has become like this. If you have a rock here, so this is what you're doing literally. This guy is pulling, this guy is pulling, this guy is pulling, this guy is pulling. You're getting what is happening? Everyone is generating dq, repulsion, repulsion, repulsion. All the pressures add up. So there is one pressure across one person there. So we will get divided by A. So dp is equal to minus EQ by area. What is E? The field inside. Remember, just now we derived rho by 3 epsilon r bar. So this will be rho by 3 epsilon r. Q will be rho A. Take it as x. Rho A dx by area. Area term gets cancelled out. So we will get pressure dp is equal to minus rho square x dx by 3 epsilon. Now, one thing you have to be careful here. If you take a sphere, what is the pressure on the open ends? What is the pressure on the surface? Is there anyone here to push it? There's no one, right? So pressure on the surface is zero. Remember this thing, the free ends and the open ends will always have zero pressure. For example, see, if I take a rod here and if I pull with this force F, यहाँ पे tension कितना होगा? Zero, right? There is no one to pull this part, isn't it? It's a free end. Logically सोचो ना, if there is a tension here, great. Who is pulling this thing here? You just can't push vacuum, right? There's nothing there. You can't pull vacuum, you can't push vacuum. Free ends have zero tension. Chalo, दूसरा logic देखो. If I want tension here, what did I do? So the tension here is pulling this much mass, isn't it? Isn't that the logic we use? So if I want tension here, whom are you pulling here? You're not pulling anyone. There's nothing there. So free ends will always have zero pressure. Be careful, quite a useful one. And this is not the first time you saw this. The first time you encountered was this problem, if you remember 22. We wrote a statement here. Here. The free ends have zero tension. So the tension here was zero actually. So the pressure on the free end, so surface में pressure zero था. There is no one to push or pull the outer surface. Remember this thing, free ends have zero tension. Quite a useful one. Remember this, we'll again encounter this in gravitation. So great, so we got the pressure. So dp is equal to minus rho square by 3 epsilon x dx, integrate on both sides. Limits will be zero. So where is the pressure zero? When x is equal to r. Pressure is P and this is x. So we get pressure is equal to minus rho square by 3 epsilon x square by 2. Limits will go from x to r. So we get pressure is equal to rho square by 6 epsilon r square minus x square. This is our pressure as function of x. At center, x is equal to 0. The pressure will be maximum pressure will be at the center. This is rho square r square by 6 epsilon. This is the reason when you go into the earth, the pressure actually keeps on increasing. So at the center of the earth, you have huge pressure. This pressure is coming because of the gravitation is crushing the planet. In this case, it is the same thing. The repulsion is trying to go away, but you're not letting it go away. So basically, this is what happened. If you look at this center, right, everyone is pushing it, from every direction. I agree, net force is 0, but the pressure is not 0. Don't get confused between net force and pressure. It's like this. If I have a block here, if I push with F and push with F, what is the net force? 0. But do you think the block will be comfortable? If I give here, let's say F 1000 F and 1000 F, force is still 0, but the pressure has increased 1000 times, isn't it? So be careful with that. Any doubts on this thing, please ask me. So this is how you do it, take an element and do this. So the idea is more important. Any doubts on this? Question still not over. What is the force on one hemisphere due to the other hemisphere? How do we do this? There are two ways to do this. Take a minute. One, we can use the pressure method and get it. Then second, I'll teach you a very interesting one. But did you get my question, what I'm asking? If I take this half hemisphere, all these guys are pushing it out. So this thing is getting repelled actually. So indirectly पूछ रहा था. If I actually cut this piece, there is a tension here which is holding the two pieces together. Is that making sense? If you make two half balls, charged ones, and if you bring them closer, they'll push away each other, right? So you need some force to keep them together. Q square by 8 pi epsilon. How did you get that? And what is Q? Let me show you the method, say. Listen carefully. So you just want the force on this hemisphere, isn't it? I already know the pressure on the surface, isn't it? What is the pressure? Rho square by 6 epsilon r square minus x square. So from the center, if I take a small circle here at a distance x, isn't the pressure same everywhere on this small ring? Pressure is a scalar, remember? Pressure का direction नहीं है. So if you can find the force on this ring and add all these rings, won't you get the full force on this cross section? And isn't that the repulsion between both of them? Does that make sense logically? If I can find the force on the thin ring and add all those forces on the rings, isn't that the total force acting on this cross section? Which is nothing but the net force acting on this hemisphere, isn't it? Because it is an equilibrium, so this force must be equal to the repulsion force. Is that argument making sense? Can you do it now? There, I gave you the idea. Solve. I'll give you a minute or two. It's an easy integration. You know pressure, you know area, just integrate and finish it off. Whatever we did today, especially the integrations ones, definitely today before sleeping or tomorrow, take a rough paper, just roughly try to do. I'm pretty sure you'll get stuck somewhere here. That is completely normal. And when you get stuck, struggle for 2-3 minutes. If you're able to figure out, great. You can't figure out, then look at the solution. Then you'll actually remember and learn much better. There is nothing wrong in not being able to do. But what did you do after that? When you didn't get the question, did you go and put a fight? That counts a lot. Let's see. So force on this strip will be pressure into area, which is 2 pi x dx rho square by 6 epsilon 2 pi. That will be r square x dx minus x cube dx. So force on that entire hemisphere will be rho square pi by 3 epsilon integral r square x dx minus x cube dx 0 to r and 0 to r. That guy will be how much? R square by 2. This is r power 4. So that will be r power by 4. So rho square pi r power 4 by 12 epsilon. Aya? The headache with this thing is first you need to find the pressure and then you have to find the force. बहुत लंबा हो जाएगा. Something interesting is there. Clear with this? Any doubts on the integration part? Once you know the pressure, I can just find the every point the pressure is changing. I can integrate and get the force. Clear with this, Sharman? Ojas? Jainil? Daksha? Clear? Salak? Got this? Ansh? Arush? Arya? Rehan? Great. Puroja, clear, na? Now look at the other one. Your favorite thing. What is your favorite thing? Do you guys know what is your favorite thing? See. So when you took this sphere, you want to find the force on that hemisphere, right? So from here, let's consider the small piece here, dq. So we took a small piece dq here. So the force on this guy will be, what is this thing? Field into dq charge. Agreed? So when I want to find the force on the total thing, this is the force on that small piece. And we already know the field E is nothing but rho by 3 epsilon into r bar. Agreed? So the force on that hemisphere or force on anything will be integral. Field is rho by 3 epsilon r bar into dq. If I take out rho by 3 epsilon common, I will end up with r bar dq. So far clear? Now we have seen something like this somewhere. If you take integral r bar dm by integral dm, this thing gives you what? R center of mass. Is that making sense? So now tell me one thing, mathematically, is there any difference between M and Q? System को तो पता नहीं है. So if I try to do something similar, so R bar dq by integral dq, this will be R bar, this will be the center of charge, isn't it? Again, why can I use here? It's a linear function R bar, देखा? Field is R bar, it's a linear function, so I can use this. The linear function is the biggest hint, boss center of mass might crop up. If I want to find the field, I can't do this 1 by r square. And the other reason, right? You can do this only inside the solid sphere. Why? Field is linear function, isn't it? बाहर नहीं कर सकते, 1 by r square है. Is that making sense? So I can replace this whole thing with integral r bar dq is the charge of that piece, right? Whatever is that, and r of that center of mass. So this function becomes simply rho by 3 epsilon, whatever the charge of that body, whatever you're taking, let's just call it body there. So whichever body you're taking, rho by 3 epsilon, r of the center of mass into charge of the body. This is a force on this, whatever body that you're taking inside. Is this clear, everyone? Now, let's go to the thing there. So what is your body here? Hemisphere. What is the center of mass for hemisphere? 3r by 8. Right? So you have to keep all the charge here, q. How much is q? Rho into volume 2 by 3 pi r cube. Is that clear, everyone? So what is the force on the hemisphere? So force on the hemisphere, rho by 3 epsilon, rho by 3 epsilon, r bar is 3r by 8, by charge will be rho into 2 by 3 pi r cube. How much is this? Rho square r power 4 by 12 epsilon. Isn't that the answer? So you can just replace whole this thing with charge here and find the force on this guy and you'll get the answer. So that is the thing. In case you don't know, center of mass is your favorite thing. How many places we saw this thing? Moment of inertia, pressure, center of mass. We saw it everywhere. This thing keeps popping up. That's why I kept telling you the center of mass chapter was a foundation. Like, that thing changed everything. Once it came, integration came. That was a game changer topic. Is the concept clear, everyone? So if you can find the field inside, and if the field is linear function, you can always use center of mass and finish off the whole thing. And the advantage of this method, right? I don't need to find the pressure, na? I literally skipped like 2-3 pages of solution and I just got it with one thing. But idea ye tha that I can do this thing. Is the concept clear, everyone?
Sir.
Nah, Vihan.
Sir, could you like explain once again what kind of element we are taking? Like it is just a slice of the area or
Chota element, this thing, na? Small dq element, negligible volume, doesn't matter. I want a point charge. Tell me one thing. If I'm finding center of mass, when you say dm, what are you taking?
okay. DQ. Okay.
समथिंग डजंट मैटर, टेक एनीथिंग ना. तुझे अगर एलिमेंट ही चाहिए ना, चलो ये एलिमेंट ही ले रहा हूं मैं.
Okay.
एरिया इज ए टेंडिंग टू 0.
Mhm.
इट डिडंट मैटर ना, कैंसिल हो गया वो.
Okay, sir.
इंटीग्रल में चला गया ना वो.
Hmm.
So in the moment you say dq, you're taking such a small piece, it is negligible size, so it's taken care of. Everyone clear with this?
Yes.
There. So today's class was important. Hollow spheres, solid spheres. We still have more varieties. We'll see them in the next class, right? We'll see shells exploding and all that stuff. We'll also have energy and everything. So next class also will be quite important. Then we'll also do something on a relation between field and potential. I think by next week we should be able to wrap up the chapter. Right, and then we'll see. After that, we'll go ahead with gravitation. Now, if you have done this much, gravitation will feel like a joke. The only thing in gravitation is the satellites. That is one thing that we don't have in electrostatics. So that satellite part is pretty good. So we'll spend more time on that. And these things we will do some problems, but you can see results sub change ho jayega directly. They're interchangeable. That is the reason I wanted to do first electrostatics. Electro is more tougher than gravity because electro may have repulsion and attraction. If you can handle electro, gravity, you'll not find it much tough. That is one. Okay, so that would be the last one for the day. We'll wrap up with this. We'll catch up again on Tuesday at 5:30. And if you see in the group, I